equations. So this is going to be a very brief introduction because we don't have a lot of time. Today we will overview some fundamentals that we need to present the topic of electric thrusters. Probably some of these things you've already seen in other classes, but so that we have everything on the same page. And if you're interested in this type of thrusting systems, I encourage you to take 16522, which is a dedicated subject on space propulsion, and it involves only electric propulsion systems. Okay, and if you have questions about today's class, you can contact me in my email, and we can either set up a time or I can answer you via email, okay? So last lecture you started on the topic of rockets. You had been doing gas turbines up to that point, and Professor Barrett explained the rocket equation, some performance parameters. I will just very briefly summarize that to begin this lecture so that I can introduce the different types of rockets that there are. I will make the classification of the types of rockets. Primarily, we have chemical propulsion systems, which will be the big part of this course, and then electric propulsion systems, which will be today and Wednesday. For us to be able to present these engines, we have to introduce some fundamentals, and this is going to be the core of today's class. So we will do a little bit of electromagnetics and an introduction to plasma physics. So the other day you derived the rocket equation. In its simplest form, the ideal case, you consider a gravity-free, drag-free space flight, and you have a variable mass vehicle, which is your rocket, that you want to accelerate to a given speed, which could be a function of time. And to do that, the only practical way to do this in space is to eject mass out of an exhaust. So we eject mass at a rate m dot c with a relative speed with respect to the rocket c, and the reaction to that momentum flux constitutes the thrust of the rocket and the propelling force, which is simply m dot c. That's the thrust of your rocket. If we write Newton's second law for that variable mass system, we have that the mass of the vehicle times its acceleration equals the force, which in this case is the thrust, m dot c. And the rate of mass expulsion, whatever propellant we're ejecting out of our system, needs to be equal to minus the rate of change of mass of the vehicle by mass conservation. So combining those two equations, we have that the mass times the acceleration equals minus the derivative of the mass with respect to time times c. And we can integrate this from an initial time to a final time to obtain the rocket equation. So rearranging this, we have dv over c equals minus dm over m. We can integrate it from an initial velocity to a final velocity, and from an initial mass to a final mass to obtain the rocket equation. So basically we have that v2 minus v1 equals c times the logarithm of the initial mass over the final mass of the vehicle. Now this change in velocity is what we call the delta v of the mission. And it's a property of the mission that we want to accomplish. The rocket equation, which is this equation here, relates us the type of engine that we need, which is given by the exhaust speed. This is engine dependent. To the mission that we want to accomplish, and here we can see that the higher the exhaust velocity, the greater the mass fraction that we can bring into orbit for a required delta V. So this is the rocket equation that you derived the other day in class. Now, other parameters that are important when we think about rockets are the specific impulse, which you also saw the other day.
Coefficient, which is the optimum and that equals you're trying to achieve a certain velocity at a certain altitude with an immense ambient pressure. Even if you have a constant static number here, so let's start by talking about the key differences between rockets and air-breathing propulsion. Momentum, its acceleration rate continually increases, so by that I mean a dot is greater than 0. So during the burn after launch. So why is it the case that even if you have a constant exhaust velocity from a rocket, the acceleration always increases? Yeah.
The force is the same, but the mass is decreasing?
Yeah, so the mass reduces and acceleration is force over mass, and so the acceleration increases. What other reasons? Yeah.
The density is decreasing.
Of the
air.
Yeah, drag reduces. What else? Think about the trajectory of the space shuttle launch. It wasn't just going straight up, right? Yeah, exactly. The cosine theta component reduces of weight. And what's the final thing? What happens when you get out into space? Sorry?
Is it centrifugal acceleration?
Well, not really, but it's just the gravity reduces, right? But it's a pretty small change. But small even to low Earth orbit. But these things are kind of just as well, because when you see even the space shuttle on launch, the initial acceleration rate actually looks kind of pathetic, right? It's barely lifting off the ground. Then it starts accelerating faster and faster, and that's because of these different factors. And it kind of takes a surprisingly long time to get supersonic. Okay, let's do a thrust analysis of a rocket. So consider a static thrust test on the ground. So we have the surface here, and we'll pin the rocket to the ground. And let's say it's sort of a crude rocket that's really a tank with a converging-diverging nozzle. So a tank with some pressure in it. And you have some jet coming out here, which leaves at speed UE for U exhaust. So we'll just apply standard control volume analysis here and draw a control volume around so that's our control surface. And the force on the control volume equals net momentum flux out. So the force on the control volume is applied, let's say it's applied here. So F, now what are the forces on the control volume? I'll say that F accounts for both this and this. Other forces?
The pressure
Yeah, pressure force, where would that be?
at the rightmost control surface.
Yeah, the exit plane here. So everything else is ambient static pressure, so that all kind of cancels out. But here you have some exit pressure, which is going to be higher than the ambient pressure probably. So plus ambient pressure times exit area minus exit pressure times exit area. Yeah. So the what I've done here is I've just considered this tube here because the static pressure everywhere else cancel out. So just this tube here, and on that tube you have PA-AE here and PE-AE here, well that's the exit area. And so that's the net force towards the right. And the momentum flux out of the control volume is just mass flow rate times exit velocity. Our thrust is m dot UEQ, ambient pressure, the momentum of the system. Delta U
velocity to a final velocity. Exhaust speed, and talking about specific impulse, is the same. It's just the which we also saw the other day, which is basically the total impulse per unit weight of propellant. Do you have a question? Oh, no, sorry. So basically we have the total impulse per unit weight of propellant, and the total impulse is simply the integral of the force in time. And the force, we said it was m dot c in time. And the weight is the gravity and times the mass. And we always use the gravity constant in Earth. If we integrate this from an initial time to a final time, and if we assume that the exhaust speed is constant, then the specific impulse is simply the exhaust speed divided by the gravity constant. So in many occasions, talking about the exhaust speed and talking about specific impulse is the same. It's just a change of units through the gravity constant, and the specific impulse takes the units of seconds. And this parameter you also saw the other day in class. The one parameter that I think you didn't cover was the efficiency of the rocket. And the efficiency will be defined as follows. If we have the rocket that we accelerate to a velocity v, and we're expelling the propellant at a rate m dot, which could also be a function of time, with an exhaust velocity c relative to the vehicle. And if we consider the system that englobes both the rocket and the exhaust, we can determine the amount of kinetic energy that that system has. So this is a closed control volume of constant mass. We're always considering the exhaust within that control volume. And the total kinetic energy of that system would be the kinetic energy of the rocket, which is 1/2 its mass, the velocity squared, plus the kinetic energy of the exhaust, which we need to integrate in time because we're expelling constantly propellant. So we integrate from an initial time to a final time the kinetic energy of that propellant being expelled, which is 1/2 of m dot, which could be a function of time, times the velocity, which is the absolute velocity of the rocket, minus the relative velocity of the exhaust, squared and integrated in time. Any question? Feel free to stop me if the pace is not right. So the total kinetic energy, if we do the derivation with respect to time, we get the total kinetic power. And the total kinetic power of our system will simply be the derivation in time of the first expression. So the first part would be 1/2 of dm dt v squared. Using the chain rule, we now need to the derivative of v squared. So we have 1/2 of m, 2 times v dv dt, plus the derivative of that integral, which is simply the integrand. So we have 1/2 of m dot, v squared plus c squared minus 2vc when we do the square of that parenthesis. Now this expression, we can simplify fairly significantly. First of all, we have that the rate of change of the mass of the vehicle with respect to time needs to equal minus the rate of propellant expulsion. So that's minus m dot. Next, we have in the second term that the mass times the acceleration, this needs to equal the thrust, which we said was m dot c. And now we can cancel a few of the terms. So the first term cancels out with this one here. The second term cancels out with the last one. And then the total kinetic power of the rocket exhaust system is simply 1/2 of m dot c squared. So this is an interesting result in that the total kinetic power of both equals the relative kinetic power of the exhaust jet, m dot c squared. And with that, we can define the efficiency of the system, which is the useful amount of kinetic power, which is the kinetic power of the jet, 1/2 of m dot c squared, divided by the power required or consumed by the rocket, divided by p, the power. And we can also write this in terms of the thrust. M dot c is the thrust, so this is equal to the thrust times the exhaust velocity divided by 2 times the power. And here we have an expression for the efficiency of our rocket.
So delta kinetic energy, the change of kinetic energy with respect to time is different from P?
Yeah, they're different. So the efficiency is defined as the power consumed, the power that you require.
Okay.
The power that is useful for that propulsive application divided by the power consumed.
Right.
And they normally are not equal. This one is smaller than that one.
Okay. Is power consumed, is that a given?
Yes, we will go into more detail in a couple of slides. So if it's still unclear, ask me then. I think it will be more clear. Yes.
Power consumed would be like m dot, like the LCV of the, like it has to do with the fuel of the rocket being used.
So the power consumed for a chemical rocket will have to do with the fuel because it will be a combustion process. That's where you obtain your energy.
Right.
For an electric propulsion system, this power will come from batteries or solar panels or things of the sort. But this is very general for any type of rocket, independent of where the power comes from. Okay? So maybe now it will become more clear. We have 3 performance parameters. These are the metrics. And different types of rockets have very different metrics in this case. And there's not one type of rocket that serves the needs of all missions. So for those missions that require very high thrust, we use chemical propulsion. So this is where they lie. In this plot, acceleration, specific impulse, but it could also be force, exhaust speed. And chemical propulsion systems have very high thrust, but this comes at the expense of low specific impulse. So chemical propulsion systems typically have their specific impulse limited to around 500 seconds. And the reason for this is that the energy available to accelerate the propellant out of the system comes from the propellant itself, from the chemical bonds of the molecules. So maybe that answers your question. If we want to overcome that limitation, we need an external power source that allows us to accelerate the propellant to higher velocities, and that's where electric propulsion systems come at play. Electric propulsion can achieve much higher exhaust speeds, so much higher specific impulse. But this comes at the expense of a lower thrust. And the reason why we have a lower thrust is that if you look at this equation here for the efficiency, the higher the exhaust speed that the engine has, the greater the amount of power that we need if we have a fixed efficiency. So in general, the thrust is limited to low values. And in this graph here, if you look at it, and if we start with this efficiency equation, we can rewrite it in terms of the acceleration as a function of the specific impulse to see how this graph looks like. So we have that the efficiency equals the thrust, which will be the mass times the acceleration, times the exhaust speed, which we said was the specific impulse times the gravity constant, divided by 2 times the power. So rearranging this, we can say that the acceleration achieved of our vehicle is equal to 2 times the power divided by the mass, so that's a specific power, times the efficiency, two times the power, and then we have it times the specific impulse to the -1 divided by gravity. So if we take the logarithm, because this plot is in logarithmic scale, we have that the logarithm of A equals the logarithm of all these values, 2 times the specific power times the efficiency divided by the gravity constant minus the logarithm of the specific impulse. So if we have a given specific power per unit mass, the gravity constant is a constant, the efficiency will be a given value. In this coordinates, logarithm of the acceleration, logarithm of specific impulse, the constant specific power curves are straight lines. So these straight lines here are derived that way. So for constant specific power, the acceleration is dependent on the specific impulse in a linear manner in logarithmic coordinates. Now, typically for electric propulsion systems, the power that we require is either obtained from solar panels, which have specific powers of this order of magnitude, the inverse of this value. So this line would correspond to the power obtained from solar panels. Or we can also obtain our power from nuclear reactors, which have a higher specific power. And then we can go to this line here. So if the power available comes from either solar panels or nuclear reactors, our electric propulsion systems must lie in this range here. There's a power limitation. If we had power sources that had higher power per unit mass, we would be able to push that envelope up. Okay. Any question? Okay. So with that, the types of rockets, chemical and non-chemical, let's go into a little bit more detail to answer your question that you had before. So basically, we have 2 types of rockets, in very general terms. First, we have chemical rockets. And chemical rockets are primarily classified this way because the energy source available to accelerate the propellant out of the system comes from the propellant itself. So the energy source, or the power available, and the propulsive mass are fully coupled, because this comes from combustion reactions. So basically, we have a combustion chamber in which we raise up the temperature of the propellant, and then we expand it thermodynamically using a supersonic nozzle to an exhaust speed C. So if we do an enthalpy balance between the combustion chamber and the exit speed, we have that the enthalpy in the combustion chamber needs to equal the enthalpy at the exhaust. In the combustion chamber, in the same way as in gas turbines, the velocities can be considered very, very small. So basically, this is the thermal energy, CP/Tc. And at the exhaust, the temperature drops significantly, so this is primarily the kinetic energy. 1/2 of c squared. So the exhaust velocity is approximately equal to 2 times the specific heat at constant pressure times the combustion temperature square rooted. So basically, for a given propellant, Cp is given, and then to increase the specific impulse or the exhaust speed, we can increase the temperature. But that temperature is normally of the order of 1,000 Kelvin. So the specific impulse typically, if we have 2,000 Kelvin for combustion temperature, the Cp of the order of 1,000 joules per kilogram Kelvin, then the Cp is the exhaust velocity is around 2,000 meters per second, which in terms of the specific impulse is a factor of 10 lower by the gravity constant, so it's around 200 seconds. So that's the typical specific impulse of a chemical propulsion system. Now, to increase that value, we need another way to accelerate our propellant, and that's where non-chemical rockets come at play. In non-chemical, we have a propulsive mass that's different from the energy source, and the energy source to provide that acceleration typically comes from either solar panels, nuclear reactors, or batteries. And there's 2 subtypes of non-chemical rockets. The first one would be thermal, and the second one would be electrical. In non-chemical thermal, what we do is we heat up the gas electrically and then expand using a nozzle. So in principle, it's very similar to the chemical rocket, but the heating up of the gas is obtained in a very different manner. So a typical example of this is what we call the resistojet, in which we have a chamber in which we heat up the gas to a temperature Tc, and we do that using an electrical resistor instead of a combustion reaction. And then we expand that heated gas using a nozzle. So it's very similar to the chemical rocket in that sense. And the specific impulses that we can achieve with these ones are not too high because we're limited by material limitations in terms of the temperatures. So to increase furthermore the specific impulse, we need a completely different way to do things, and this is where electric propulsion systems come in. In electric propulsion systems, we use electromagnetic fields are used to accelerate the propellant. And we have either electrostatic accelerators in which the force is transmitted electrically, or electromagnetic accelerators in which the force is transmitted magnetically. So in this case, we need a gas that is responsive to electromagnetic fields, and that typically either requires to have charged particles, ions, or what we call a plasma. Any question? No questions? In Wednesday's class, we will derive the performance parameters of electrostatic thrusters. That would be lecture 18. Okay, so if questions, let us give a few values or orders of magnitude of what performance parameters we're talking about. So the performance of electric thrusters, we said they have high specific impulse, so that translates into propellant savings through the rocket equation. But this happens at the expense of small forces. And because we have small forces, we typically thrust during very long times as compared to chemical rockets. So in this table here, which is a little bit dated, I'm sorry for that, we have different types of rockets and their typical performance parameters. The first two rockets are thermal non-chemical. The resistojet is when we heat up the gas using electrical resistors. The arc jet is similar in concept, but now instead of having an electrical resistance, we have an electrical arc. The ion engine is what we will do in lecture 18, and this is the classical example of an electrostatic thruster. Then the magnetoplasma dynamic is the one example of electromagnetic. And just for comparison, the last rocket is a chemical example. So here you can see that the thrust of chemical rockets is fairly high, and this is a very small rocket. It's hundreds of newtons. Whereas for electric propulsion systems, the thrust is of the order of a newton. 2,000 millinewtons is the largest value quoted there. On the other hand, the specific impulse for chemical is very low, 200 to 150 seconds. And for electric, it can be orders of magnitude higher. There we have a factor of 20 for the ion engine, 5,000 seconds. On the other hand, chemical rockets operate for very short times of the order of minutes or hours, whereas electrical thrusters operate for months or even years continuously. So very different operation, very different propellants used. For chemical, we use hydrazine for a monopropellant rocket. For electric, we typically use noble gases, xenon, argon, things of the sort. So basically, they cover or they serve very different missions. Yes.
For the thermal
Yeah.
engines, if you were to have an achieved period, like if you had that nuclear.
On the other hand, the specific impulse for chemical is very low, 200 to 100 of the order of minutes or hours, whereas electrical thrusters operate for months or even years continuously. So very different operation, very different propellants used. For chemical, we use hydrazine for a monopropellant rocket. For electric, we typically use noble gases, xenon, argon, things of the sort. So basically, they cover or they serve very different missions. Yes.
For the thermal
Yeah.
engines, if you were to have, like, is that the maximum specific impulse that you can achieve, period? Like, if you had that nuclear reactors superheating a gas?
Well, here the problem is that you're heating up a gas, so materials cannot withstand temperatures higher than certain values. So even if you had more power to dump in there, you would be constrained by other types of limitations, which would be thermal limitations. Yeah.
So that's just like materials limited.
Yeah. In this case, yes, it's the same as for a combustion chamber. You're limited by materials. Yeah. And there's other types of rockets that are not here. This is what we work on in the Space Propulsion Lab. I see some people here have been working in our lab. Electrosprays, if you ever hear about them, or field emission electric propulsion systems. These are new families of electrical thrusters that are used for micropropulsion applications. They're electrostatic in nature, but they operate very differently to the other plasma engines that we will see. and they can produce very, very small thrust levels, and that's the beauty behind them. Any question? Yes?
Sorry, what's the thing written next to ion engine?
Oh, this is just that it's going to be the topic of lecture 18.
Oh, okay.
Thank you. Okay. So with just brief summary, depending on the performance parameters, different rockets are suited for different applications, and in particular, electric propulsion systems are suited for missions that either have very high delta V or long operational time. And that's just because of the consequence of the rocket equation that the higher the specific impulse, the less propellant that we need to accomplish the mission. So if the delta V is high, we might as well use a rocket that has a high specific impulse. Examples of missions that can greatly benefit from electric propulsion system are those that are long in nature, that need continuous forces to be delivered. North-south station keeping in geosynchronous orbit, basically maintenance of the right inclination of the orbit at all times. So this needs thrusting over the whole lifetime of the satellite, on and off. Interplanetary travel, again, for the propellant savings. If we're going very far away, we will require high delta V, and therefore we can benefit from electropropulsion. Micropropulsion systems are the way to go for very high precision or very small forces, because we can go down to micronewton level. And finally, there's other types of missions that can be done with either type of rocket, but it's done very differently. We use chemical rocket or electric rocket. So for example, if we're doing orbit racing, we have a satellite in LEO orbit, and we want to go to geosynchronous orbit. If we do this using a chemical rocket, we will have high thrust, but short firing times. So the way we go from a low Earth orbit to a higher orbit is to give an impulsive maneuver in the initial orbit. This transfers us to an elliptical trajectory that takes us to the higher altitude orbit. And then to circularize that orbit, we give a second impulse at the apogee of that elliptical trajectory. And this is what we call a Hohmann transfer that basically requires two impulsive maneuvers. And I think you will cover this type of trajectories later on with Professor Barrett. Now, if we do this using an electric propulsion system, we now have very low thrust levels, but we can fire continuously. So typically what we do is what we call a spiral climb. The pen is not working properly. So basically we start with a trajectory that slowly raises continuously the circular orbit until we get to our destination. So the mission analysis design for each kind of engine is very, very different in each case. But we can do it either way. Okay. Any question? So if there's no question, let's do a little concept question to finish up this part of the lecture before we go into the fundamentals of electropropulsion to fix some ideas. Okay. So compare the amount of propellant needed for a given mission with a delta V of 500 meters per second. If we use an electric thruster with a specific impulse of 2,500 seconds instead of a chemical rocket that only has specific impulse of 250 seconds. So typically, how long do you?
Normally wait until the total results goes up to about 30.
Ah, okay.
That means most of the students have answered.
Oh, okay. Okay, most of you got it right. The propellant mass savings are a factor of 10, and it's much better in that sense to use electropropulsion systems than chemical rockets. Anyone want to tell me how they came to that conclusion? Anyone that answered this one?
You can use the ISP to find out the C, which is the velocity, and then from that, if you plug it into your equation, you can see that the exponent term decreases by about 10 times the negative exponent term.
Great. So that's the right answer. Basically, if you plug it into the rocket equation, the propellant savings are of that order. So I'll just write it down here so that you have it in your notes. If we go from the rocket equation, we have the final mass over the initial mass equals the exponential of minus delta V over C. And now the final mass is simply the initial mass minus the propellant mass. So we can obtain an equation for the propellant mass, which is 1 minus the exponential of minus delta V over C. And if we assume that delta V over C is much less than 1, which is definitely true for the electropropulsion system, not so much for the chemical rocket, this is equal simply to delta V over C. So the ratio of propellant masses is the inverse of the ratio of the specific impulses. Since those are a factor of 10, this is a factor of 10. So the chemical propulsion system consumes around 10 times more propellant than the electropropulsion system. Now, the gains in reality are not as big because we need to carry, well, what was that? So that one doesn't have an electric propulsion system. So basically, the gains are not so big because we need to carry power supplies or solar panels or things of the sort with us. So the savings in total mass are not as big as a factor of 10, but maybe a factor of 6 would be more realistic. Okay. So this was a little bit of an introduction comparing chemical rockets